There is a significant announcement in the world of computer science that changes how we understand information itself. An IBM scientist has recently been recognized with a Turing Award, the highest honor in the field, for fundamentally rewriting the rules of information processing. This is not just about a new tool or a faster processor. This is about a shift in the mathematical bedrock upon which our artificial intelligence systems are built. The research in question links concepts from physics directly to the neural networks that power modern machine learning. It suggests that the future of scalable data architectures relies on understanding energy functions and associative memory in ways that were previously considered purely theoretical. Here is the thing. For decades, the development of neural networks was driven by trial and error and massive computational power. We threw data at algorithms and hoped they would find patterns. The winning research introduces a different paradigm. It treats the learning process as a physical system seeking equilibrium. Think of a ball rolling down a hilly landscape. The ball does not need to know where the bottom is. It simply follows gravity, moving toward the lowest energy state. In this new framework, a neural network is viewed as a system where every connection between neurons contributes to an overall energy level. When the network learns, it is essentially minimizing that energy to find a stable solution. This is the core algorithmic shift. It moves us from brute force calculation to guided optimization based on physical laws. Now consider this implication for your own data architecture. When you are designing a machine learning operations pipeline, you are usually focused on moving data from point A to point B. You monitor latency, you track throughput, and you ensure the model retrain cycles run on schedule. But with this new understanding of information theory, you can start treating the data pipeline itself as an energy system. You can design your machine learning operations infrastructure to minimize the energy required to maintain model accuracy. This means that when you ingest new data, the system does not just store it. It evaluates how that data shifts the energy landscape of your model. If the new data causes the energy to spike, the system knows it is encountering a distribution shift or a drift in the data quality. This allows for a more proactive approach to monitoring. Instead of waiting for a model to fail, you watch the energy function climb and intervene before performance degrades. This approach also changes how we think about hardware accelerators. The research highlights that the same mathematical principles enabling powerful AI also dictate the design of the chips that run it. If you understand the energy function of the algorithm, you can design the hardware to support that specific minimization process more efficiently. This creates a feedback loop where software and hardware are co-designed from the ground up. For a scalable machine learning operations pipeline, this means you might choose different storage solutions or compute resources based on the energy characteristics of the model you are deploying. You are no longer just fitting a model to a server. You are fitting the server to the mathematical nature of the model. Another critical aspect of this award is the recognition of interdisciplinary work. It signals a shift in how the Turing Award is awarded, increasingly favoring pioneers who established the mathematical and physical rules of information processing over those who merely implemented existing tools. This suggests that the most valuable work in the coming years will happen at the intersection of fields. Merging statistical mechanics with computer science is becoming critical for solving complex information processing challenges. If you are building next-gen data architectures, you should be looking beyond standard data engineering practices. You should be asking how the physical constraints of your storage and compute layers interact with the logical constraints of your learning algorithms. There is a surprising finding in this research regarding associative memory. The early theoretical work on energy functions was initially seen as abstract physics. It was not immediately obvious that it would become the bedrock for modern deep learning and neural network training. Yet, it is exactly this non-obvious trend that is driving current capabilities. The recognition implies that we are moving away from treating AI as a black box of weights and biases. We are moving toward a state where we can analyze the stability and robustness of a system using the same tools we use to analyze physical matter. This gives us a new vocabulary for discussing reliability. We can talk about the stability of a model in terms of its energy basin. We can talk about generalization in terms of energy barriers. For the practical engineer, this means your integration strategy needs to evolve. You cannot simply drop a new model into an existing pipeline and expect it to behave. You need to account for the energy dynamics. This might involve adding layers to your pipeline that calculate these energy metrics in real time. It might mean adjusting your hyperparameters not just to maximize accuracy, but to minimize the energy required to maintain that accuracy. It is a shift from optimization for performance to optimization for stability. This is particularly important for scalable systems where a small drift can cascade into a major failure across thousands of nodes. By aligning your machine learning operations practices with these fundamental rules of information, you build systems that are not just faster, but more resilient. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.